Hello students, today we will discuss about the torque acting on a current carrying loop when it is placed in a uniform magnetic field. So see here in the diagram I have drawn here. So I have taken a uniform magnetic field here. This is the two pole pieces, this is north and this is the south. Okay. So as we know the magnetic field moves from what? North pole to the south pole. So this is the direction of the magnetic field. Okay. So this parallel what lines indicating this is a uniform magnetic field. Now, in this uniform magnetic field, we have kept a rectangular coil A, B, C, D. This is a rectangular coil. So here as I have written here, AB equals to CD and the length we have taken that is L. Okay. And BC is equals to AD. So its width it's taken as what? B. Okay. So this is the rectangle. So its side length are given to us. Okay. So this y dash is the axis about which this coil is turning or it is rotating. Now here this coil is carrying a current I and we can see this is the direction in which the current is flowing. Now we have to find the torque, but we know whenever a current carrying that conductor is placed in a uniform magnetic field, it experiences a force. Now if you look at this rectangular coil, it is consisting of what? 4 different pieces of conductors which is carrying current and that is placed in a uniform magnetic field. So that means all the 4 conductors what we have seen here, or you can say the 4 section of this coil, all will experience the force. Okay, let's see what is the force experienced by the each section here and what is its direction. So let's consider first this AB. So one more thing is that let's suppose this coil which is placed, its normal vector, you can say its area vector. So area vector is what? This is the outer drawn normal to this coil or plane of the loop you can say. So this is the n cap, this is the outer drawn normal, or you can say this is area vector. Let's suppose this area vector of this loop is making an angle theta with the magnetic field. Okay, so here area vector is making an angle theta with the magnetic field. Now we'll find out what is the force experienced, okay, by each section of this loop. Now first if we'll consider this AB section and the CD section, look at these two sections AB and CD. So they are what? Right angles to the magnetic field, because the magnetic field is moving like this or this is acting in this way, and AB and CD both are what? Right angle to this magnetic field. So that's what. So we can find first for this AB section. So for this AB if you are saying, so let's suppose the force which is acting here is represented as F1. And we know when a conductor placed in a uniform magnetic field, the force value is given as what? Or F equals to I L cross B. Okay, so that we can put here. So this F1 equals to, this is I L cross B, or that's equals to what? I L B sine theta. This is the formula, ILB sine theta. And in this case, what is the theta value? Theta is actually, that is the angle between what? That is the L vector and the what? That is magnetic field. And I said what? This L vector and the magnetic field, for this case is making what? Angle 90 degree. So here since theta equals to 90 degree, so what will be a F1's magnitude here? So this will be equals to ILB, because sine 90 value equals to 1. So that's what, so this is the magnitude of F1. But what will be the direction of this force? So to find the direction, since it is making an angle of 90 degree, that's L vector is making an angle of 90 degree with the magnetic field. So to find the direction of the force, so we can use this Fleming's left hand rule. So here if we'll apply for this AB section, if I'm using Fleming's left hand rule, so see here the first, or you can say that the first finger of this left hand, that is giving you what? That is a magnetic field, right? And this is the middle finger, gives you what? The direction of the current. Then the thumb will indicate the direction of the force. Now same thing here, apply, let's apply here. So this is first finger, it is indicating the direction of the magnetic field, and this will be giving you the direction of the current. So current, you can see it is moving up like this. So that means what is the direction of this magnetic field? So here, sorry, that force. So what is the direction of the force here? So this is the direction of the force which is moving inward. Okay, so here ILB moving into the plane of paper, into the plane of paper. Okay, and perpendicular to what? And perpendicular to AB. Okay, so it is perpendicular to this AB conductor and it is into the plane of paper. Okay, so this is about F1. Now similarly, let's find out for CD. Because CD, why we are finding? Because same case will be there, because CD is also making an angle of what? 90 degree. So here, let's suppose this force is taken as what? F2. In case of CD, the force what we have taken, so let's suppose F2. Now here, the same thing. So formula of F2 will be ILB sine theta. Now this is also, this will be giving you what? ILB, because here also theta equals to how much? This is theta equals to also 90 degree. And what is the direction of the force? Here you can see the magnitude is coming the same, because the same current is flowing. The length of AB and CD are same. So that's what. So you can say this is ILB. Sorry, here this is capital B, that is the magnetic field. Okay, so this is ILB sine theta. So here ILB, now we have to find out what is the direction of this force F2. Now let's apply this same here. We have to apply this Fleming's left hand rule for this case. So as I said, this first finger is pointing the direction of the magnetic field. So this is the direction of the magnetic field. This middle finger pointing the direction of the current. So current, you can see in the CD arm, it is moving down. Now this thumb will indicate the direction of the force. So where it is indicating? It is moving out of the plane of paper. So it will be coming out. So this is F2's direction. So here it is what? ILB, moving out of the plane of paper. And perpendicular to CDR. Okay, it is perpendicular to CDR and it is coming out of the plane of paper. So look at what is that. So we know what is the magnitude of force formula. Magnitude of force formula is what? I L cross B, where L is the length of the conductor and this is the what? Length vector, and this is B. B is the magnetic field. So what is the magnitude? This is ILB sine theta, you can write. Okay, ILB sine theta. Now the same thing when it is applied here. So this is for this AB section, current flowing is I. What is the length of this section? That is L. And what is the magnetic field's magnitude here? That is B. So ILB sine theta. But in this case, since AB is making an angle of 90 degree with the field, so theta is 90. So that's why this is ILB. Over, and its direction is what? Into the plane of paper. Now similarly, if you look at for the CD section, CD is also having length L. It's also carrying the same current I. Okay, and it is in the magnetic field B. So that's why in this case also the same thing you can get. So that is ILB. But only thing is that direction of the force will be what? It is moving out of the plane of paper. Now we'll discuss the rest two arms which is left here. Okay, now we'll discuss the arm that is BC. Look at the section BCR. Okay, so in that case BC is not making 90 degree with this magnetic field. So that's what. So in this case, let's suppose the force is taken as F3, and F3 will be equals to what? That is I, that is L cross B. But here what is this BC's length? That is BC or AD is taken as what? B. So I'll write this is I B cross capital B is the magnetic field. So this is the thing. So or it will be IBB sine theta. Okay. Now here IB cross B. So it will be coming as IBB sine theta. But the thing is that we need to find out what is the direction of this force. Now to find the direction, we can use this Fleming's that right hand palm. So not Fleming's only. So we can use this right hand palm rule to find the direction in this case. Otherwise you can go that is right hand screw rule. So that also can be utilized for that one. So let's suppose I am using this right hand palm rule to find the direction of force in this case. So here, so according to this, the statement is what? If you just stretch your right hand, okay, palm, and if the stretched fingers, it is indicating the direction of the magnetic field, the thumb is indicating the direction of the current, then the that face of the palm will be indicating the force direction. So that means here in this section BC, now you can see that the magnetic field is what? It is moving like this way, north to south. This is the direction of the magnetic field, and this is pointing the direction of this current. Now current is this one, so that means it is the current's direction. That means the palm is facing upwards, so that means you can say the force F3 is acting in the upward direction. So it is upward. or you can say this is along the y-axis. Okay, so this is acting like this way. Now similarly, we have to apply the force for the, means we have to find the direction of the force and also its magnitude for this arm AD also. So here in case of AD, so let's suppose the force experienced by this is F4, and in this case also this is I, B cross B, because here also the width is B, so this is B cross B. Now let's find out its direction by using the same right hand palm rule here. Okay, so here, so I'm stretching this fingers pointing the direction of the magnetic field, right? And what is the direction of the current? Current is this one, so that means I have to go in this way. So that means you can say this is the direction of the magnetic field, this is indicating the direction of the current, then in which direction this is facing? It is facing downward. So that means the force F4 will act in the downward direction. So this is acting downward. So we got all the four forces in their direction. Now look at these forces F3 and F4. Their magnitudes are coming same, right? Their magnitudes are same. And if you look at the direction, they are just opposite. One is F3 is acting upward and F4 is acting downward. So both are opposite to each other. And if you look at their line of action is same. The two forces, they are acting along the same line, okay, but in opposite direction. So that means here F3 is equals to minus of F4. So that means both are having the same magnitude and they are also acting in the different direction, or not different, that is opposite direction, okay. And their line of action is same. So in that case what will happen? Both the forces which what they are going to cancel each other. So that means F3 and F4, F3 and F4. So this will cancel each other. So that means net force along this direction will be what? 0. Now we'll talk about, so since these two are cancelled, what? They are cancelled by each other. Now only the two forces are left, that is F1 and F2. So we'll discuss about them only. Now look at, if I draw its side view, so here you can see that, so here the two forces we got, F1 and F2. Okay, so I'm showing here, let's suppose this is the direction of the magnetic field, right? And the two forces are acting in this way. So this is one force which is F1 and this is the another force which is F2. Okay. So let's suppose this is the outward drawn normal, okay, to the plane of this coil. So this is actually the plane of the coil which we are seeing from the top view. So actually this is the top view of this. Okay. So when you look at from the top, it will be, that coil will be appearing like a what? A straight line like this way. Okay. So this is, so you can say let n cap, this is the area vector which is making an angle what? Theta with the magnetic field. Okay. So this is your diagram. Now we have to find the torque. Why? We have to find the torque over here. Look at these two forces what we got, F1 and F2. If you can see that F1 is equals to, that is ILB magnitude, if you look at this F1, and if you look at the magnitude of F2, this is also ILB. Both are having the same magnitude and their directions are not along the same line of action. Okay, they are acting in opposite direction but not in the what? Same line of action. So in that case, these two equal and opposite forces, they are constituting what? A couple. And when a couple acts, so in that case what? Means when the couple will be there, so there will be a torque will act. And now we have to calculate what is the torque which is acting on this current carrying loop. Okay, so that's what we have to find the torque. Now, what is actually torque's formula? Now the torque, tau formula is what? That is either force into perpendicular distance between them. So this is the formula to calculate the torque value. So either the force, because both the forces are having the same magnitude, ILB, okay, but since the line of actions are different, so they are constituting the couple which is what? Tries to rotate the what? Rotate that coil. And that is what the torque is. So we are finding that moment of that force, that is which is called as what? The torque. Now we have to calculate the torque as the formula I said, either of the force into perpendicular distance. So the magnitude of the force is known to us. Only thing is that we need to calculate what is the perpendicular distance between them. So look at how to calculate this perpendicular distance. Now see, since this is the plane of the slope, right? And this is the area vector's direction, and what angle it is making? 90 degree. What is area vector? So this n cap is what? This is a outward drawn normal. So that means what? With the loop, it is making an angle of what? 90 degree. So that means with this one, so it is making an angle. Suppose this is AD. Let's suppose this is AD. Okay. So with AD section, it is making an angle of what? 90 degree. If this is theta, then what will be this angle? So this will be equals to what? 90 minus theta. Okay, this angle is 90 minus theta. Okay, so here, now let's reduce it backward. So that I can join here. Let's suppose this point is O. And here you can see this is the direction of this force F1, or you can say this is the line of action of this force F1, and this is the line of action of this force F2. And the perpendicular distance between them is what? OD. So this is the perpendicular distance between them, and that we need to calculate. Now look at what is the length AD. So length AD is actually what? That is B. So that means this one, this length is B. So that means AD equals to B. So that is known to us, right? Now look at, if this is 90 minus theta, now this and this line is what? That is parallel. So here you can see, okay, look the picture here. So this line is parallel to this line. Now this is acting like a transversal. So this angle is 90 minus theta. So what will be this angle? So this is also 90 minus theta, right? And this is 90 degree. Okay, because it's a perpendicular distance here. So that's what? So this is 90 degree. So if it is 90, this is 90 minus theta. So what will be this angle? So this angle will be theta. So that means look at the triangle AOD, what we got. So if I redraw this triangle, so we got like this way. So this is A, this is D, this is O, this is 90, this is theta. And this is 90 minus theta. So that is not necessary. So look at, this is theta, this is, okay, 90. Now what is the length AD? So length AD is what? That is B. The length AD is, that is what? B. And here along this direction force F1 is acting. Along this direction this force F2 is acting. So in between these two force line of action, the perpendicular distance is which one? That is OD. We need to calculate OD. Now if I am taking sine theta, so using the triangle, so from triangle AOD, so I can use this triangle, this right angle triangle AOD. So look at this one, AOD, right angle triangle. So what will be sine theta? Perpendicular by hypotenuse. Now what is perpendicular here? That is OD is the perpendicular. So OD divided by AD. Okay. Now actually we are trying to find out the length of OD. So what is OD from here? So OD will be equals to AD sine theta. Okay, so it will be AD sine theta. But what is AD? AD is B. So that's what? This is B sine theta. So we got the value of what is OD, and OD is nothing but your perpendicular distance. So that means here we can write down tau is equals to that either force. Now what is the force value? That is ILB into what is the perpendicular distance between them? It is coming around. This is B sine theta. Okay. Or this can be written as, this is ILB B sine theta. Okay. Now what is L into B? So that is the area of this rectangle, because length into breadth gives the rectangle's area. So instead of LB, I can write this is capital L. This is B sine theta. Okay. So this is IAB sine theta, and that is what the torque which is acting here. So tau equals to what? IAB sine theta. So that means if the coil is having only one turn, then in that case the torque acting here is what? That is IAB sine theta. Now if suppose the coil is having n turns, if the coil is having n turns, okay, n number of turns, that means each turn will carry what? This much, means they will be having, or they will experience this much torque. So that means what will be the net torque acting on that? So in that case, total tau will be equals to, that will be n I a b sine theta. Tau will be equals to NIAB sine theta. This is how we can calculate what is the torque acting on a current carrying loop when it is placed in a what? Uniform magnetic field. Now it's different cases if we look at. Now the case 1, if theta equals to 0 degree. If theta equals to 0 degree. So if you remember what the theta I said you, theta, you can see the picture what I have drawn here. Theta is the angle between what and what? That is the area vector and the magnetic field vector. That is the angle between the area vector of the coil and this is what? The magnetic field vector. So that means if theta is 0, in which case theta will be 0? If the coil or plane of the coil, if it will be held perpendicular to this field. So if it will be perpendicular to the field like this, suppose this field is acting in this way and the coil is held like this perpendicular to this field, the plane of the coil will be placed perpendicular. Now in which direction its area vector will act? Area vector will be what? It will be acting in this way because it is the outward drawn normal to that. So if it will be outward drawn normal, so this is the direction of the magnetic field, even this is the direction of your n cap. So in that case, what is the angle they will make? So that will be what? 0 degree. So that means if theta 0 means what? You will understand. It means the plane of the loop is held perpendicular to the magnetic field. Okay, so this is the meaning of theta 0. So theta 0 when it will be, if the what plane of the loop will be what? It is perpendicular to the magnetic field. In that case, its area vector will be making an angle of what? 0 degree with the magnetic field. And in that case, what will be the torque will be acting here? This will be tau equals to NIAB sine 0. And what is sine 0 value? That is 0. So that's why in that case, the torque acting will be 0. So here, so that means there will be no torque acting if the, or you can say it is a minimum torque acting, or you can say no torque acting when the loop is held what? At right angles to the magnetic field, or it will be making, means its area vector will be making 0 degree with the magnetic field. So this is the case 1. Next, second case we'll discuss here. Now if theta equals to 90 degree. So what is the meaning of theta 90? So when it will be, that means if the plane of the loop is held parallel to the magnetic field. Okay, so that means if it will be, suppose this is the magnetic field and the plane of the loop will be held like this way. Okay, so it is parallel to the what field? In that case, if I draw a normal to this area vector, that direction of the area vector will be making what? 90 degree with this. Okay, if the plane of the loop is like this way, so that means it is held parallel to this magnetic field. So its area vector's direction is this one. So area vector with the field, it will be making an angle of how much? That is 90 degree. And in that case, tau will be equals to what? That will be NIAB sine 90. And what is sine 90 value? That is 1. So this will be the maximum torque it will experience, NIAB. So here tau will be the maximum value. In which case, if theta is coming to be 90 degree, or you can say if the coil or the loop which is carrying current, it must be placed what? Parallel to the magnetic field. Okay, so this is what the torque acting on a current carrying loop and its different cases.